Okay, Newton's rule that we talked about, which was the limit as h approaches 0 of the function a plus h minus f of a all over h. So his rule, it tended to work best. It favors polynomials, and it favored trig expressions. So it tended to just, the math was easier. So Leibniz's rule that we also talked about last week. So the limit, and you know, it was kind of an equal split on your test, like half of you chose Newton and half of you chose Leibniz. It's fine, because it worked for both. So, whoops, hang on. Not h approaches 0. Okay, as b approaches a. And then we have f of b minus f of a over b minus a. That tended to favor functions that were exponential, logarithmic, rational roots, and functions with asymptotes. Okay, so those were the two rules we talked about. Then you've got our good friend, the power rule, which covers everything. All right, so the power rule for derivatives, which can pretty much cover all of those. It doesn't cover trig and doesn't cover exponentials and logs. We'll have separate rules for that, but it will cover polynomials, rational roots, and asymptotes. And so our power rule said if you could express your function in terms of a power. So how does that work for, like, square roots? Can you express a square root as a power instead? Sure. What power? 1/2. Sure. Okay. Same thing for asymptotes. That would work too. You could write that to the -1 power. All right, so if you've got that, then the derivative, so the notation is either prime or df dx. Those are the two notations which mean that you've done the derivative. The prime was the notation favored by Newton. The df dx, that means it's read, Newton would read f prime of x, which is his derivative notation. Leibniz would read df over dx, or the derivative of f with respect to the variable of x. So those were their two notations, and then the rule went like this. The power was pulled to the front, so it became n multiplied by x. And then the x was reduced in its power by a value of 1. So that's the power rule. So what I'm going to do is show you an example right now. I'm going to show you a Leibniz example, and then we're going to confirm it with the power rule to show that you get the same thing either way. In your homework, the first 3 questions you need to prove with the power rule, prove with Leibniz and confirm with your power rule, and then for all the rest of the homework, you can use power rule the whole rest of the way. Okay? So here we go. Let's do one where we're going to prove it with Leibniz, confirm it with the power rule, and then we can put these proofs to bed. If f of x is the square root of x, find df dx, which is the Leibniz notation. Okay, so find out what that derivative is going to be. So because I see df dx, the proof needs to be in Leibniz form, and then we'll confirm it with the power rule, show that the power rule worked, and then we'll be done. So df dx in Leibniz's method would be the limit as b approached a of the square root of b minus the square root of a over b minus a. The way you do this with Leibniz is to use the idea of a conjugate. Right now you have the subtraction of rad b minus rad a, and we're going to multiply that by its conjugate. And so it's the conjugate of that is the opposite sign. So we're going to take rad b minus rad a over b minus a. And the conjugate is going to be rad b plus rad a. And I have to multiply the top and bottom by the same thing. So we're mathematically multiplying by 1. When you multiply the top and bottom by the same thing, that's legal because you're not changing anything, because anything times 1 is itself. But we're doing it strategically, multiplying the front by the back to see what we get. When you multiply by a conjugate, it simplifies to b minus a, because we'll get rad b times rad b, which is b. And then we have the two center terms, which are going to cancel out, rad ba minus rad ba, and then minus the square root of a squared. And so that would be over the denominator then, which also had b minus a in it, but still has the leftover part of the conjugate. And so what we end up with is a reducible situation. We end up with the quantity b minus a in the numerator that can be reduced with what was previously in the denominator. So those two things will reduce, leaving me with the limit of b approaching a of 1 over the square root of b plus the square root of a. And since b is approaching a, we can replace b with a, so we'll get 1 over the square root a plus the square root of a, which is 1 over 2 times the square root of a. And so the derivative of the square root function, according to Leibniz, is proved to be 1 over 2 rad a. So we're going to confirm that using the power rule. And so the power rule would say, all right, f of x is the square root of x, which could be rewritten as x to the half. So anytime you want to confirm it, just rewrite it in the expression where it's got a power instead of how it was written before. And so then f prime would follow the power rule, which would be 1/2 x, and then the subtraction of 1. And so I have 1/2 minus 1 becomes negative 1/2, which is 1/2 times 1 over rad x, which is 1 over 2 rad x, which was the same thing I got doing Leibniz's way. I just had a instead of x. So your first 3 problems are like that. Do Leibniz, confirm with the power rule, and from there on, the rest of the homework, you may use the power rule the whole rest of the time. Okay? All right, so you will have 20 minutes to get started on this homework.